Okay, so let's start today's lecture. So last time we started this slide set number 6. So let's see where we are. And it is continuing with the same convolution. So linear system and convolution. So initial slides will just be saying what we'll be discussing here. And we saw already that for continuous time, what is convolution, and for discrete time, what is convolution. So this is convolution for discrete time, where it means convolution sum, and we have seen actually the order doesn't really matter, but it is basically this convolution sum that you see right here, the summation. And for continuous time, the convolution actually means convolution integral, which is this x of tau, h of t minus tau. Again, the order doesn't matter, we can take h of t first or x of t first, it is our choice. Now we can either have your impulse response to completely describe your system or to completely find out the outputs for any given input, or we could be given difference equation in order to find out output for any given input. Till now we have been focusing on convolution, which is based on impulse response. So if impulse response h is known, we can find out output for any given input. Now the impulse response for any given difference equation can be found if you have an FIR system, just like you see right here. So if you have an FIR system, we can just replace x of n with delta n, and we will end up getting the impulse response, because then input becomes delta n, output becomes h of n. So we can directly do this. So these types of things we have seen earlier. It is just a quick review. Here it says that we may end up having non-linear system with the same impulse response, but because we are not dealing with non-linear system in this course or throughout your undergrad, so we will not consider that. So we will stick to linear systems, where from your difference equation we can find out the impulse response, and we can do convolution and find out output for any given input. So these are the properties. We saw these properties earlier, that this convolution order doesn't matter. Did we cover it last time? Any volunteer? Did we cover these properties? So did we cover the properties of convolution and initial few things? I believe we did in the last lecture. Okay, so continue with the properties. So we have seen that the order of convolution doesn't really matter. We can take any one first and accordingly get convolution sum. And the other properties, and this is true for both discrete time and continuous time, the order doesn't matter. We can take any term first, either h of t first or x of t first, and accordingly get convolution integral or convolution sum and find out the result. This is what we saw, that if you consider the property of convolution, the distributive property, it helps you simplify parallel systems. And what is that distributive property? We saw it last time, that it is very similar to the property that we have for a multiplication operator, just like we have a multiplied by b plus c. So this is same as saying that a multiplied by b plus a multiplied by c. So we say that this multiplication operator has distributive property. Same you can see right here, your convolution operator also have the same distributive property. If you are trying to convolve x of n with sum of h1 and h2, it is same as convolving x of n with h1 plus convolving x of n with h2. It will give you exactly the same result. And this is true for both continuous and discrete time. And as I mentioned, all these properties that we are going to consider will be valid for both continuous and discrete time. And this distributive property that you see here is used to simplify your parallel systems. So if you have parallel system like that, so we can just replace it with an equivalent system. And the parallel system is having, let's say, one system is having impulse response h1t, the other system having impulse response h2t, and we are just adding the results together and getting yt, then we can just simplify these parallel systems into one equivalent system whose impulse response h of t would be sum of the impulse responses h1t plus h2t. How do we get that? If you see output here y1t, it is going to be x of t convolved with h1t, and similarly if you see y2t here, it will be x of t convolved with h2t, and if you see the result, it will be basically this plus this, sum of these two, y1 plus y2. And what we can do is we can just write that whole thing that you see here, same thing is written right here, x of t convolved with h1t and x2t convolved with h2t. First one is your y1, the second one is y2. So if you have this type of situation, what we can do is we can just simplify and write it like this. It is x of t convolved with the sum of these two, and the sum of these two, we can take this as your h of t. So we can simplify your parallel system into a single equivalent system, and this is valid not only for two systems in parallel. We may have more than two systems in parallel, maybe 3, 4, 5. All we need to do is we will just sum up all the impulse responses of parallel systems and get one equivalent system. So this is the distributive property that helps us in simplifying your parallel system and finding one equivalent system for that. Next, I believe we also saw the associative property, which helps us in simplifying. I'm sorry, is there a question? Is there a question? So if there is a question, please repeat. I was not able to clearly hear that. Okay, so I assume there was no question. So if we see the associative property, it helps us in simplifying serial system, and this is what associative property is. If you are trying to convolve three things, convolution actually takes two terms, so we have to convolve two terms first, and then the result will be convolved with the third term. So if we have to convolve, let's say 4, 5, 6 things together, so we have to take them two at a time. And this is that associative property, that order in which we do convolution doesn't really matter. We can convolve these two together and convolve the result with x of n, or we can convolve these two and then convolve the result with h2. So this is the associative property, very similar to the property that we see for multiplication operator. So either we have this or we have this. Both of them mean the same thing. So this actually helps us in simplifying your serial or cascaded systems. So if you see here, if you have two systems in series, one having impulse response h1t, the other having impulse response h2t, what we can do is we can just have one equivalent system for these parallel, for these series systems, and its impulse response h of t would be given by the convolution of h1t with h2t. So this is what we saw, I believe, in the last lecture also. I'm just quickly reviewing the same thing again. So this is what your associative property is, valid for both discrete and continuous time. And similarly, if we just continue, so these two properties together, associative property and your distributive property, helps us in simplifying complex systems which have multiple systems patched together in series or parallel. We can just have one equivalent system for that. And how we reduce that is by using your associative and distributive property and coming up with an equivalent single system. Okay, so system with memory, system without memory, we covered that also. A memoryless system is a system whose output depends on present input only. Example is that amplifier system that you see. The output is basically scaled version of your input. So whatever input is there, your system just scales that input and gives you your output. And you will see that the impulse response for these Amplifier type systems would be very straightforward. Just replace x of n with delta n, and yn becomes h of n. So impulse response becomes a single scaled impulse. That's an impulse response. And memory systems are those systems whose output depends on preceding values of x or past values. Really find out those systems are. Isab, do you have any question or your mic is turned on by mistake?
क्यों?
Isab Khan, can you hear me? Okay, so let me continue with the same thing again. So memory system would be having these values x of n minus 1, x of n minus 2, or y of n minus 1, n minus 2 in the difference equation. To compute your output, you would require your previous inputs or previous outputs in your difference equation. That will become a memory system. System invertibility, this is the interesting thing that we saw. If you have two systems which are, let's say, inverse of each other, so second system is sort of undoing the effect of first system, then we say that if you have two systems in which second system actually undo the effect of the first system, we say that second system is inverse of the first system, and the first system is a system which is invertible. So this will be an invertible system whose inverse is h1t. And in that case, the output that you get, y of t, would be same as the input, x of t. So this is what we saw for system invertibility for inverse systems. Now we have already seen that if you have two systems in series or cascaded together, we can just replace it with an equivalent system whose impulse response h of t would be given by the convolution of these two impulse responses. So if you have two systems h1t and h2t, their equivalent would be just convolution of h1 with h2. So if we want that your system should be equivalent, system should also give us the same thing, that y of t should be equal to x of t, then you would see that the convolution of these two systems impulse response will end up giving you delta as a result. So the convolution sign is missing here. That was what I pointed out last time also. So it is basically if you have two systems h1n and h2n which are, let's say, inverse of each other, then the convolution of these two will end up giving you delta n. And the same is true for continuous time also. Okay, and this actually led us to another important factor, which actually says that if you convolve anything, output we know y of t would be x of t with ht. So this property actually also led us to another important thing that we found out, that convolving anything with delta t gives us the same thing back. And we actually solved that and showed you also that how that happens. You can just in this case take the convolution integral and you will see that you will end up getting the same thing back. And same is true for discrete time also. If you convolve anything with delta n, you will end up getting the same thing back. That means x of n convolved with delta n will give you the same x of n back. Accumulator system. This accumulator systems are systems which actually accumulates or sums up all the inputs that are there till that present time. That's an accumulator system. So typically we write accumulator system y of n as k equal to minus infinity till your present time x of n minus k. That's an accumulator system, and if you expand this summation, it ends up becoming x of n plus x of n minus 1, and it goes on and on and on and on. That's an accumulator system. It accumulates all the inputs till present time. Okay, so again we can have an inverse of accumulator system, and this system that you see here, that's an inverse of accumulator system. In previous lectures we showed that instead of writing this accumulator system as this summation, we can also write it as y of n is equal to x of n plus your previous output. So all previous output, whatever was previous output, we add your present input to it and get your present output. So it is sort of an accumulation going on. So this difference equation actually describes your accumulator system, and this equation also describes your accumulator system. Both are one and the same thing we saw last time. So this system and this system, these two are going to be inverse of each other. You will see that this is the difference equation, and its impulse response, if you want to find out, just replace x with delta, and your y becomes your impulse response. So this is the impulse response for inverse of accumulator system. Causal property, we saw systems are causal if their output depends on, or y of n depends on, all the inputs or outputs till present time. It does not depend on any n plus some term. So that is a causal system, and all the real world systems are causal in nature. Stability, I believe that was sort of the last thing that we did, that how do we find out whether a system is stable or not, and I actually solved all that separately also to show that how we can actually check whether a system is stable or not. First of all, how do we define a stable system? We define a stable system as a system which takes bounded input and gives bounded output. So a bounded input gives bounded output. So if input is not infinite, output will never become infinity. So you can keep giving bounded inputs and you will keep getting bounded outputs. So till the time your inputs are not infinite, your output will also not become infinity. So that's how we define a stable system. A system is stable if every bounded input produces a bounded output. And to check for stability, what we can do is we need to check whether this is true for that system, that a bounded input is giving a bounded output or not. And for that, we actually put a bound on the input. We said that, let's say your input does not exceed a particular finite value b. This value is always less than b. It has an upper bound, and this b can be any value, low, high, whatever, but it's a finite value. So x of n, if it remains within an upper bound b, then we'll check whether your output also remains within a bound or not. So output of any system is basically convolution, and again, as we said, convolution order doesn't really matter. We can take h of n or x of n first, whatever. And this is basically convolution sum, k equal to minus infinity to infinity, h of k, x of n minus k. So this is the output for any system. Now, if we take the value of y of n, that means we are taking value of this, and this is what we see right here. So output value is basically the value of this convolution sum. Now we have seen that your x of n value does not exceed this upper bound b. So if you take the value inside this summation, that is value of h of k multiplied by value of x of n minus k, or magnitude of this and magnitude of this, then you see that this symbol equal to symbol gets changed to less than equal to, because this summation does not put a limit on positivity or negativity. But if we put a mod here, that means we are always taking the positive value. So this product will always be a positive product, and that will end up making this summation either equal to this or greater than this. That's why we put this sign right here, that if we take this magnitude thing inside, then this equal to sign gets changed to greater than equal to. Now this value actually is the value of your input, and we know that whatever inputs are there, it is always supposed to be below certain bound B. So if we, instead of having any value, we put the max possible thing instead of this, then again the product that you will get, if you just replace it by B, the product of B with this will again be greater than or equal to your value of y of n, and B being constant, we can take it outside your summation. So we end up getting this, that your y of n magnitude will always be less than or equal to this product right here. This is some constant. Now this summation that you see right here, it is actually dependent on the impulse response of your system, and this is basically your sum of impulse response. Now if this summation is finite, only then this product will be finite. So if this summation that you see right here, if this summation is finite or less than infinity, then this product will be less than infinity, and only then would be your magnitude of y of n less than infinity. So this is actually showing you that in order for this y of n to be always within a certain bound, you will, what we want is that we should always be having this summation less than infinity, or having a finite value for this. So this is the condition for stability, that your impulse response should be, as we say, absolutely summable, or in other words, impulse response summed should give you a finite value. Now this was for discrete time, this was convolution sum. If you do the same exercise for continuous time, you will see the end result would be that your impulse response has to be absolutely integrable. Instead of this summation sign, you will end up getting this integration sign of h of tau, d tau. If this integration is less than infinity, only then you will see that your system would be stable. And again, the examples for two very simple systems, one is basically a pure shift system, the other is basically a system whose impulse response is step impulse response. We saw these two systems. Now this h of n is basically just a simple shifted impulse at n equal to n naught. So this is your h of n. So if you want to check whether this type of system having impulse response, which is a single impulse, is that stable or not, all we need to do is we need to have summation of h of k. That means summation of impulse. Now if you have summation of impulse for k equal to minus infinity to infinity, we know that this impulse has value only at n equal to n naught. At all other points this value is 0. So if you open up this summation and put in different values of k right here, so you would see that its value will exist only at k equal to n naught, and that point its value is 1. Rest all are 0. So this summation is only going to give you a single value, which is 1, which is finite value less than infinity. So we say that your system is stable. Now if you take a continuous time thing, in continuous time, if you have again a shifted impulse lying at t equal to t naught, so this is your delta t minus t naught. So if you have this type of a thing, then if you take integration of this h of tau, so h of tau is what? Delta, instead of t we have tau here, so tau minus t naught. If you integrate it, over the entire interval from minus infinity to infinity, you would see that for the whole range of tau from minus infinity to infinity, this delta or impulse will have value 0. Only at tau equal to t naught, its value will be equal to 1. And that is what is shown right here. And otherwise also I said, I think in the previous lecture I showed you this, that if you have an impulse inside a summation or inside integration, whether it is a shifted impulse, whether it is an impulse lying at origin or n equal to 0 or t equal to 0, it will always give you a single value. So if you have impulse lying inside a summation or integration, you can just directly see it and write the answer. So both of these we found are stable. Continuous time also and discrete time also are stable things, because we saw that in case of this one, the discrete time thing, we found that your h of n was absolutely summable. And for continuous time, we saw that it was absolutely integrable. Or in other words, summation gave us finite value, and here for continuous time, this integration gave us a finite value. On the other hand, if you see these systems again are sort of a IAR type of a system, where it becomes equal to 1 at n equal to n naught and remains 1 all the way to infinity. So this is what we have right here. And if you want to sum up, just seeing it, we already know that we are trying to sum up infinite number of ones right here. So it is definitely going to give us infinity. Otherwise also, if we just take sum of h of k for k equal to minus infinity to infinity and replace h of k value from here, so h of n is this, h of k would be u of k minus n naught. So this is again step. Whenever we have step inside a summation or integration, it just changes the limit. So what limit change it will give? The way I would do it would be, we know that this particular step signal is 0 from minus infinity all the way to n naught, and only from n naught all the way to infinity it becomes 1. So it would be summation k equal to n naught till infinity, it is 1. The value is 1. And if you are trying to sum up infinite number of ones, you will see the result would be infinity. And similarly, if you see the other one, the second one is also an IAR, infinite duration thing. So it's a step signal starting from t equal to t naught. So this is your h of t. This is your h of t. T going all the way to infinity. Just seeing it, we know that area under the graph, if we try to see here, it's going all the way to infinity, so area will become infinity. So integration definitely will give you infinity, but if you just still want to go through it, it is basically h of tau, and we can just replace the value of h of tau, it becomes u of tau minus t naught. And we know if we have this step signal inside any summation or integration, it just changes the limit. The way I would do would be, so this step signal is going to be 0 all the way from minus infinity till t naught, and from t naught till infinity it is going to remain 1. So the limits will become from t naught all the way to infinity, and it remains 1 within that range. And this is basically integrating this, and this is going to give you value equal to infinity. So area under this graph is going to give you value equal to infinity. So both of these are unstable, both of these are stable. So we actually, I believe, covered till this point, and very quickly going over the differential and difference equation. We know that differential equation describes the relationship between input and output for a continuous time systems. Whenever we want to write an equation which gives us relationship between input and output for a continuous time system, we end up invariably getting a differential equation. And this differential can be with y, can be with x, we can have any order of differential present. So But in any case, a differential equation actually is an equation which gives us the relationship between input and output of a continuous time system, or it completely describes your continuous time system. In comparison, if you have a discrete time system, the equation which gives you relationship between input and output for a discrete time system invariably will end up becoming a difference equation. And you may have difference terms with y, difference term with x. It all depends on what system you have. So we saw this example in shape of a RC circuit. We always assign the outputs as y and inputs as x. So even if the output was, let's say, voltage across a capacitor, input was voltage, source voltage, so we are not very concerned with whatever that thing was. We just assign the variable y to the output and variable x to the input and write equations in terms of x and y. That way it becomes much nicer to look at and much easier to deal once we are doing all the arithmetic and solving it. So later on at higher level courses, you will be seeing that how we can come up with equation for any given systems, and how can we correlate equation with systems. But in this course, we are actually having the introduction of what's a differential equation, and then just taking input as x and taking the output as y. And we are not concerned in this course for what that system was, whether it was a machine, some machine going on, or some electronic circuit, or whatever it was. Similarly here, we are concerned with the difference equation for a discrete time systems. Now whether that system describes let's say bank accounting or whatever, we are not very concerned with that. So we already saw what's a differential equation and what's a difference equation, and these actually completely describe your system, and related to that is basically your impulse response. In this course, we will be mostly focusing on the impulse responses for your systems, because there we'll be using the concept of convolution and finding out output for any given input. Although we could use your equations also to do the same thing. Now, just looking at these equations, just examining the systems or looking at these equations, we can relate them to system properties. We can just see the equation and see the properties of the system that is these equations actually represent. Now, if we take continuous time system, the differential equations can be generally written in this shape. We can take all the y terms on one side and all the x terms on the other side. Now the y terms may have few of your differential terms also, and you may end up getting something like this, a naught y of t, and on this side we may have something like this, b naught x of t plus b1 dxt by dt. So coefficients a with y terms coefficient b with x term, and generally your equation will be something like this. You will have few terms here and few terms there. It all depends on what type of system you have. In generally, if you want to write this in shape of summation, it will be something like this, where you have some order of differential equations on this side. Here you see the differential we have with the y of t is 0 order. This is first order, and we may have higher orders present or may not have those present. Similarly here, if you see this is 0 order differential with x of t, first order differential with x of t, second order, third order, fourth order. So your differential equation will be something like this. And the order of differential equation actually is the highest differential present in your equation. And example is right here. So if we see, this is a differential equation which is having, this should be a naught. So this is having a naught here and this is A1. So if your A0 is 1, if A0 is taken as 1, and typically we always take A0 as 1 just to make sure that we have y of t clean. Even if you have any value here, we just divide both sides with that and make sure that your yt remains, coefficient of yt remains 1. So typically we take A0 equal to 1 or keep A0 equal to 1. And whatever other coefficient is, that actually determines the property of your system. So if you see this system, if A0 is equal to 1 and we have some term, some value for A1, you would see that if you solve this differential equation, you will end up getting a result something like this. And that actually shows us that your system is infinite impulse response. Otherwise, also just seeing this differential equation without even trying to solve it, we can just see the differential equation and judge whether you have an FIR or IIR. In this particular case, we have already talked about it earlier once we were discussing the properties of system. If you see any differential of y present in your difference equation, first order, second order, third order, then we say that we are having a IIR. But if your difference equation has differential terms with x and no differential terms with y present there, then we say that you are going to have a FIR. Example of FIR would be a difference equation of this type. Y of t is equal to 0.5 x of t minus, let's say, 0.1 dxt by dt. So here we see we have a differential term present with x but no differential of y present in your difference equation. So this will be your FIR system. Here we see differential present with y, and here even the x term is not shown here. So this is going to give you an IIR. Even a single y differential term present will make your system IIR. Similarly, if you talk about difference equation, we can group all the y terms on the left hand side and we can group all the x terms on the right hand side. So let's say we have this A0 y of n, and here we have A1 y of n minus 1, and we have all these terms here equal to B0 x of n plus B1 x of n minus 1 and other terms. So it will be typically of this type. Difference equation will be typically of this type, and we can just sum that and write it in this shape. So all the coefficients of y's are a, all the coefficients of x are given the symbol b. And example is shown right here. And here also you will see that typically we always keep this A0. We keep this A0 as equal to 1. We keep A0 equal to 1. And here we see that we have this y of n and A1 y of n minus 1. And you will see that this will again be a IIR. Because we talked about this earlier also, once we are talking about properties of the system, that even if you have a single feedback term, any term with y of n minus something present in your difference equation, then we say we will end up getting a impulse response which is infinite in nature. Example of FIR, we have seen so many, but let's give another example. If you have a term like this, so it has difference present for x but no difference terms for y. So feed forward terms are there but no feedback term. So this is going to end up giving you a system which is having impulse response which is finite. So summary, whatever we covered in the summary part is shown right here. Okay, so this is something that we have already covered. So let's just continue and see what we have further present. Let's just see few examples here. Now in The remaining part of this lecture, few minutes we have now, and the two lectures that we have tomorrow, we're just going to first do few, you can say, examples so that we are comfortable with the concept of convolution and we are sure that how we can do convolution. There are many methods in which we can do convolution, and we will see that what all those methods are. I will just be focusing on three different types of methods. Although if you are following any videos from YouTube or maybe following any courseware from MIT or Stanford or whatever, you will see that there are more than 5, 6, 7, I don't know how many methods that can be used for doing convolution. I will not limit anybody from using any method as long as it is the right method. So just feel comfortable and just practice different methods and see that what method suits you more. So okay, just let me first talk about the differential and difference equation. Let me give an example of a difference equation. Now if we see difference equation, just looking at it, we should be able to say multiple things about the properties of the system itself. And I believe I did that exercise earlier also, but let me quickly go through it again. So if you are given this equation, again as I mentioned, for mathematicians this is a difference equation, but for engineers it's a system, discrete time system, something like this, having an input and an output. So for us it is a system whose difference equation actually tells you this. Now just looking at this equation, we may say a few things about the properties of this system, that what type of system this is. Now a volunteer, can any volunteer give me property for this, any single property? What is the property of this system? Any volunteer?
Time हो गया.
Okay, that's not a property, that's an observation. So can anybody give me a property of this system? Are you guys even there? You just log in and just don't respond. Any volunteer, give me a property for this system. It's a discrete time system, so give me any property for this system. Did I ask you guys by name?
FIR system.
Okay, so finally one volunteer gave me FIR system. So can somebody explain why it's an FIR system? It is right, it's an FIR system. Why is it an FIR system? How do we know that this is an FIR system? No response. Why is this an FIR system? So, okay, we'll just does somebody want to respond to that? Why is this an FIR system?
सर इसमें s की जो x की टर्म है ना उसमें n-1 आ रही है प्रीवियस टर्म.
Okay, Atazaz. Well, you're right. So we are having feed forward terms only. We are not having any feedback terms. So this difference is present only in the x term. So this is a FIR because of that. Okay, so we can say that this is FIR, and as I mentioned, FIRs are always stable. Your IIR may or may not be stable but if it is an FIR, it will always be stable. Next, this is a first order system. Next, we don't see any n plus term present here, so it's a causal system. So you see that just by looking at this equation, we were able to say so many things: FIR, stable, first order, causal. Now specifically, these are very important for us. These two properties that you see, 1 and 2, these are very important for us because causal systems, all the real world systems are causal. If your system is anti-causal or non-causal, it cannot be a practical real system. We cannot patch it up. We cannot make a circuit for that. So if you come up theoretically with a very nice system with a very nice response and it is serving your purpose, but you find that the difference equation, looking at difference equation, you find that it is not causal. That means that system is more of a theoretical system. You cannot make a circuit out of it. Second thing, if let's say it is causal, but it is not stable, even then there is no point making a circuit out of it or making or patching it up, because it is not going to be stable. So it is not going to give you your desired result. So these two things later on, especially in DSP, we will be focusing on these two properties, that we will always be focusing on causal and stable systems. And if it is FIR, we know it is always stable. So I will just stop here. Okay, before I leave, any questions?